good morning to this, the fourth session of the Mexican meeting. And today, I have the pleasure to introduce Professor Antonio Asin. He's coming from the Institute of Photonic Sciences from Spain. And he will talk about something about the quantum information. Please.
Okay, so good morning, everyone, and thanks for being here, and thanks Moises and the organizing committee for the invitation. So so today I'm going to tell you in general terms about a new type or new approach to quantum information applications that for this, say, general public talk, I prefer to name it as quantum information theory with black boxes. And it's also one of the main research interests in my group in Barcelona. So I'm leading the quantum information theory group at ICFO, the Institute of Photonic Sciences in Barcelona. So I've been told that this is a talk for people who may not know much about quantum information theory. So in my talk, I will explain things basically from scratch. So it may be that if you know about quantum information theory, some of the things I'm going to say are familiar to you, but I hope it will allow that we all proceed on the same track. So let me just start by a general consideration about what quantum information theory is about. So basically, the main goal of the field is to answer this question, which is what happens when you encode information on quantum particles. And so it's just a sort of transition that the information devices are doing now. So they are going from our macroscopic world that we describe with Newtonian physics, and they are entering the microscopic world, the atomic world. And I always like to make an analogy with something that happened at the end of the 19th century, beginning of the 20th century. So at that time, experimental physics was reaching the atomic world with some experiments like the photoelectric effect, or they were touching things that you need to understand what is happening with light at the single photon level, or you need to understand what happens at the atomic level, okay, like the spectra of atoms. And at that time, it happened that the tools that people had to describe physics were revealed to be not enough to describe these new experiments, and this is why theorists had to design a new theory, which was quantum physics. Okay, and then, well, first they tried to explain things, making some very weird hypotheses like quantization of light and things like this, and then Heisenberg and some others came, and then von Neumann, and they formalized the theory, and now we have quantum theory that we all know, all physicists know. Okay, so, and this was a revolution in physics. So physics really, there was a dramatic change in the way we understand nature after quantum physics. Okay, so this was this revolution at the level of our understanding of physics. So now, one of the main points of my talk is that we are experiencing a similar revolution, but now for information devices. So now our information devices are smaller and smaller. So I don't have to say many things about this. We all see this in our reality. Many of us have a smartphone. And this is an amazing computing device that is very small, that possibly some of you are checking now at the moment, in spite of me giving this talk. But, okay, we all see that we have these smaller and smaller information devices, and this is just happening because we are able to put information in smaller and smaller scales. Okay, and this is why we can put much more information than before in smaller scales. We have smaller information devices, and what is going to happen is that we are going to put information on the atomic scale, and then we will reach atoms, and we know that atoms, if we want to describe atoms, we have to use quantum physics. So the natural question is, what happens when we encode information on quantum physics? Okay. Also, another thing that I always want to remind when in this first slide is like, I think this, okay, at the moment it's not clear where quantum information theory will lead information devices, but I think there is a first change in the way we understand information. So if you had asked me, okay, I'm a physicist, but I also have a degree in telecommunication engineer. Okay? So if you had asked me, when I finished my telecommunication engineer degree, if you had asked me whether the fact that you use quantum physics for information processing had implied any change for information processing, I would have said no. Okay, because one of the nice things about information, the way we understood information, is that it was completely unrelated to physics. Okay, so information is just about, I mean, what is a bit? A bit is something that you do with two alternatives. You encode a 0 and one alternative. I can send you a bit with my hotel key and this pointer, right? I can send you a 0 and a 1. Of course, we don't do it like this because this is very unpractical. But from a point of view of information theory, from a logical point of view, there is no difference. So physics doesn't seem to play a role, okay? But what we know with quantum information theory is that physics does play a role. And the fact that you change the physical laws that describe your information devices implies a change in the things you can do with information devices. So what are the things that we can do? Well, I mean, what we know now is that there are some computing devices that are more powerful than our computing devices based on classical physics. And we have a new form of cryptography. Okay, so physics matters. And in my talk there is quantum computation, so this means that there are more powerful computers based on quantum physics, but for my talk I'm going mostly to focus on quantum cryptography. Okay, and quantum cryptography, sometimes you may have read, if you have read something about quantum cryptography, that it provides unbreakable private security, private information exchange. So what is cryptography? Cryptography is the art of securing private information transmissions. Okay, so people, when deriving the first quantum cryptography protocols that I'm going to tell you about, they said that they provide unbreakable security. Okay, so let me just go on and then explain about quantum cryptography. So I'm going to give you some very small mini courses on some of the concepts I'm going to explain during my talk. So now I will give you a very short course on quantum cryptography. Don't be afraid, quantum cryptography is something super simple. Okay, so especially if you know about quantum physics. But I think even if you don't know about quantum physics, you can understand the main idea of quantum cryptography. But I will assume that you know some quantum physics in what I'm going to say. So I will illustrate quantum cryptography by the simplest protocol, or not the simplest, the first protocol that was proposed by Bennett and Brassard. So Bennett was working and is still working at IBM, and Brassard is a computer scientist in Canada, and they proposed this protocol in 1994. So the idea is that I want to send you some message. So I want to exchange some private message with Moises, and to do that, we will use a key. So the idea is that we have a key, and we use this. I use this key to encode the message. I send this message through the channel. Since it has been encoded with the key, it cannot be read. And Moises has the same key as me, and then he can undo the process and read the information. So this is secure. But of course, in a way, it's a way of cheating, because I'm assuming that Moises and I share the same key. So how do we establish this secret key? You can say, okay, we met before. But if we met before, we exchange the message. Okay? So if we have a key, we can exchange information. Now the problem is how we establish a key. And what is a key? A key is something very simple. It's just a list of bits that are random in the sense that it cannot be predicted by my enemy, and that they are perfectly correlated. So whenever I have a 0, Moises has a 0. When I have a 1, Moises has a 1, and so on and so on. Okay? This is a key. And it's secret in the sense that it cannot be predicted by someone else. So the protocol is just a key distribution protocol using quantum physics. So what these two researchers propose is the following. So in cryptography, usually people talk of Alice and Bob. These are the honest players that want to exchange private information. And what Alice does, she wants to establish the key with Bob. So what she does, she generates a random bit. She tosses a coin. And depending on the result, she chooses to encode the result, and she can prepare what is called a qubit. So for a qubit, it's nothing but a quantum system with 2 degrees of freedom, a spin 1/2 particle, for instance. Okay, and this is the qubit. It's just, if you know about the Bloch sphere, I'm just representing the spin 1/2 particle by the direction of the spin. So she can encode the information, the 0 and the 1, that she has generated in a spin particle pointing into the plus z, or plus x, minus z, or minus x. So for instance, if Alice got a 0, she will encode into either plus z or plus x. She chooses randomly between any of these two states. Okay, so she prepares this spin 1/2 particle with a spin pointing, let's say, in the plus z direction. She sends this particle to Bob, and now Bob chooses to measure in the z or x direction. And he will read the result and extract the information according to the same table as Alice. Okay? Now, I hope you know some quantum physics, but quantum physics tells you that if Alice prepared, say, something pointing in the z direction, and Bob decided to measure in the z direction, he will read the information without any mistake. Okay? This is textbook quantum physics. So this means that if Alice sends a 0 in the plus z direction and Bob measures in the z direction, he will get result 0 and he will write a 0 here, as Alice wanted to send. Now, however, Bob does not know in which basis Alice encoded information, so sometimes he measures in the x direction. And if you know about quantum physics, if not, I can tell you, if you measure a state that has been prepared in the z direction, you measure in the x direction, you will get result plus and minus with probability equal to 1/2. And this means that you know nothing, okay? Because you can get the same effect by just throwing the state and tossing a coin. Okay, so in half of the cases, Bob is lucky and chooses the same basis and gets the same result as Alice wanted to send. And in half of the cases, Bob is unlucky and he doesn't know anything about what Alice wanted to send. Okay, it's not super efficient, but this is not a big problem because now Bob can announce which basis he used for the measurement. So he can say, Alice, I measure in the z basis. And Alice can say, good, keep it. And if Bob says, Alice, I measure in the z basis, in the x basis, and Alice uses z for the encoding, Alice will say, throw it away because the result is not reliable. Okay, so they keep those bases where they use the same basis because they are reliable, and they throw away the remaining cases. So at the end of this process, you understand that, okay, it's not super efficient because in half of the cases they will throw away some of the symbols, but for those symbols that they keep, whenever Alice sends a 0, Bob has a 0. Whenever Alice sends a 1, Bob has a 1, and so on and so on. And this looks like the secret key. Okay, so it's a list of bits that are perfectly correlated. Well, this is not entirely true because for sure this is a list of bits, but I have somehow to prove that it's secret. I didn't say this is. I could have obtained the same by just sending 0s and 1s to the channel. Okay, so I have to prove that it's secret. So if I say something about secret, I have to introduce the third party in any cryptographic protocol, which is the enemy, the eavesdropper, who wants to read the information. Usually this is not my choice. The enemy is called Eve. Okay, so Eve is the enemy who wants to read information. So she's here. So Eve is, as soon as something leaves Alice's laboratory or location, Eve can take everything. Okay? But she has to give something to Bob. Bob is expecting a photon or a spin 1.5 particle to arrive from Alice. So Eve is intercepting the particles, doing something with them, and forwarding something to Bob. So, and now here comes the brilliant idea by Bennett and Brassard, okay? So what's the problem here? Eve is somehow in the same situation as Bob. She has to read an information that has been encoded either in the Z or the X basis. These are non-orthogonal bases, okay, for those, these are non-orthogonal states, if you know about quantum physics. And then there is something called Heisenberg uncertainty relation in quantum physics that tell you that you cannot distinguish between, you cannot perform two non-commuting measurements. You cannot measure in the Z and X basis at the same time. I hope you know about this principle because it's something well known, okay? So Eve doesn't know whether she has to measure in the Z or X basis, so she cannot read the information. And if she does it, she will perturb the information. And of course, those who will agree about the basis are Alice and Bob, not Alice and Eve. And this is why Eve cannot read the information because it has been encoded on possibly two non-commuting bases. And this is why I can say that it's a secret key because the enemy cannot read the information. Okay, so I hope more or less you understood the idea. Quantum cryptography, in a way, for this form of quantum cryptography is Heisenberg uncertainty principle in action. You just exploit this principle. And here it comes perhaps one of the first messages of my talk, which is that I think sometimes when I give a talk, people ask me, is it quantum cryptography better or worse than classical cryptography? Well, I prefer quantum cryptography. This is why I work on quantum cryptography. But what it has to be clear is that it's something different. So what is classical cryptography? Our standard classical cryptography, the one we use to encode our information, is based on what is called computational security. So the enemy, we assume that the enemy, okay, she's super powerful, but her computational power is limited. So she cannot have a computer that is as big as the Earth. Otherwise, we will see it. Okay? So she has a big computer, maybe a supercomputer, but not an amazing computer. So her power is limited. So what you do to secure information, you use a problem which is difficult to solve with any computer on Earth. And the standard problem is factoring. So there are problems that are super difficult at the moment to solve. So you use this problem to encode information, and you assume that since the enemy computational power is limited, she cannot solve this problem, hence she cannot read the message, which is something very nice. Okay, so what are the problems? In my view, okay, let's see, what are the weaknesses of these schemes? Well, the first, I think the main weakness is that there is no proof that there are difficult problems. Okay, so maybe you know a question that is called, is P equal to MP? Okay, this is a complexity theory problem that wants to know whether there are difficult problems for a classical computer. So this is not known. So for instance, most of our encryption schemes are based on the fact that it's difficult to factor. So what is factor? If I give you 6 and I ask you 2 factors that multiply give 6, everyone knows this, 3 and 2, yeah, right? 3 times 2 gives 6. But this is a problem that becomes very difficult. I can give you a very large number. It's very difficult to find the factors that solve this problem. And this is the problem that is used for our encryption schemes. So we all live happily with this. We believe that this is secure. Now, if tomorrow a researcher finds an algorithm for efficient factorization, these schemes become insecure, because there is no proof that there is no efficient algorithm for factorization. So if someone tomorrow publishes a paper, this is the end. But it might be even worse, because it could be that this person finds the algorithm and doesn't publish the paper. And we keep using these algorithms. Okay, so it's a weakness. We believe that they are secure because human beings, very smart researchers, have tried to find an algorithm and they have failed. But there is no proof of not existence of this algorithm. On top of that, a quantum computer can factorize numbers efficiently. So if someone has a quantum computer, can factorize numbers and can read this information. Okay, we believe there is no quantum computer because it's technologically demanding, but there will be one possibly in the future. Okay, so there's a risk. So what is quantum cryptography? It's something completely different. Again, I'm not saying it's better or worse. Okay, it's different. So you base things on physical security. So now you don't care about the computational power of the eavesdropper, but what you assume is that whatever she does, her action is explained and it's limited by quantum physics. So in particular, she cannot break Heisenberg's entity relation. Okay? Otherwise, she could even get the Nobel Prize, let's say, for physics, okay, if she could break quantum physics. So whatever she does is limited by quantum physics, and based on the validity of quantum physics, you prove the security of the protocol. So the nice thing here, for instance, is that you assume the validity of quantum physics, and then you can strictly prove security. Okay, so this is a difference with the previous case. Okay, so very nice. You see, I'm giving you this talk, I'm telling you that there is quantum cryptography, things are unbreakable, it gives you new possibilities for encryption. And people were writing papers. I was even writing papers where I was saying a new form of unbreakable security. There are even nowadays, you can even secure your information transmissions with quantum cryptography. There are companies that sell you quantum cryptography. But some years ago, there were some group of people, in particular the researchers led by Vadim Makarov, you know, he really looks like the quantum hacker. So who were able to, they went to the company, they bought a quantum cryptography product, and they hacked the product. Okay, and well, of course, it got some attention, and they appear published in Nature Photonics, in good journals, and people were interested. And somehow it was a surprise, okay, because in principle, this form of cryptography was unbreakable, and this is what I was telling you in a way. Okay, so am I lying to you? Okay, what is happening here? So how come? Okay, the good thing about hackers is that Makarov is a good hacker. So he wants to help people to understand the limitations of a scheme. So hackers' attacks are always good for cryptography because we learn about weaknesses in encryption schemes and we improve. And this happened also in this case, okay? So I was telling you before that quantum cryptography is secure because it's based on quantum physics. And we thought at that time naively that if you want to break quantum cryptography, you have to break quantum mechanics. You have to prove that quantum physics is wrong. But we were wrong. And in fact, Makarov didn't show that quantum physics was wrong. He didn't break the principle of quantum cryptography. He broke the implementation. So by this I mean the following. So if you remember the protocol I explained to you, this BB84, I was telling you have to encode information on spin-1 hard particles that are sent from Alice to Bob. So the theory tells you that the protocol should prepare states spin-1 hard particle. What is a spin-1 hard particle? It's a quantum object that lives, for those who know about quantum physics, that lives in a Hilbert space of dimension 2, which is in the mathematics that we use to explain quantum physics. And then you have to make these measurements that are spin-1/2 measurements, that are self-adjoint operators on a Hilbert space of dimension 2. And this is what the ingredients that you know to make quantum cryptography. Now you go to the lab, or even to the company. Well, the company has to prepare a state that is living in a Hilbert space of dimension 2. I don't know how someone can even certify that something is living in a Hilbert space of dimension 2. So what you will do, you will input information on a photon, and perhaps on polarization. But how do you know that you are just encoding information on 2 levels of this photon, okay? Or this atom? I mean, it's impossible to guarantee anything like this. I think if you think carefully about it, it's impossible to certify that you are encoding information only on 2 degrees of freedom. Because you can never exclude that there are some accidental encodings of information in other degrees of freedom. So I think this is an hypothesis that is needed for the protocol that is very difficult to meet in practice. And also, I mean, and you go to the provider and you'll say, oh, look, you have to make a protocol, you have to prepare single photons and put information on polarization. And the provider will tell you, well, look, I mean, single photon is something very expensive. Do you mind if I use an attenuated laser? And you say, well, why not? Let's try to do it with this. But this is not the single photon that you need for the theoretical security proof. So a mismatch appears between what the theory demands, where the protocol is defined, and what you do in the lab. And perhaps you have a security proof that you can prove that the protocol is secure in the theory, but this is not what is happening in reality. So you need a proof that it's secure here, where you have to take into account all these possible weird things that can happen in reality. And it was precisely this mismatch that the hackers used to break the protocol. So it would be very nice. I mean, in a way, it's very nice to have protocols based on physical security, but if you rely a lot on the physics of your devices, this may open loopholes for your security. Okay, so this was a problem, and the second problem is something that is common to classical and quantum cryptography. This is common to any cryptographic application, which is certification. And here it's good to illustrate this with some of the papers, documents that became public with the Snowden affair. So I guess you all know about Snowden, where some documents by NSA were made public. And in one of these documents, it was clear that the National Security Agency was promoting an encryption scheme because they knew how to break it. So they were saying, please use this scheme, because they knew afterwards how to break the scheme you were using to secure your messages. And the bad thing is that this scheme that was promoted by the National Security Agency was certified to be secure by NIST, by the National Institute of Standards and Technologies, I think, okay, by NIST. And somehow NIST is an institute that we used to trust, okay? And it's not that NIST, they were bad or they were our enemies. They just took the encryption scheme, and it looked secure for them, and they said it's secure, so people were using this scheme, but NSA was able to hack this scheme, okay? So this is a problem. When you buy a cryptographic device for someone, you are trusting that this person is helping you. So you put trust on this person. And in fact, RSA, which is the company that is based on factoring, was saying, please stop using this protocol because now we know that it's not secure. So do we always need trust? When you go to a provider and you buy a cryptographic solution, do you always need to trust that this person has implemented what he's supposed to implement? For cryptography, do we know that this person has, for quantum cryptography, has encoded information on quantum particles? I mean, think about it. When you go to a provider, you get a box. You say, give me a quantum cryptography, and the provider will give you a box. And then you have to say, is this quantum? And the provider will tell you, yes. This is what you get. And a price, of course, you have a price for this. And I always use this joke to illustrate this problem of certification, which is also connected to my talk, okay? So perhaps you know this cartoon, Dilbert. And here is the problem of certification. So again, I always put the same example. So he wants to be sure that this is a proper random number. And this is the random number generator is producing this sequence, okay? Well, it doesn't look random, but you know that the probability that a proper random number generator produces this sequence is the same as any other sequence, okay? And the guy says that, well, this is a problem with randomness. You can never be sure. But as you will see, you can be sure in quantum physics about something is random. Again, this can be the random number generator that the provider is selling you. Okay, this can be this daemon or just a box. You go to a provider and say, I want a random number generator, and it gives you box. Okay, so some years ago, we proposed a solution to this hacking and certification problem, which is the following. And I was kind of telling you about this, okay? So think about it. When you go to the provider, what the provider gives you is a box. So if you want to do protocols and you don't want to care about what the provider has done in the box, it's better to do protocols where you see the devices as boxes. So you don't make any assumption about what is happening inside the box. In standard cryptography, quantum cryptography, you have to assume that the box is preparing states living in a Hilbert space of dimension 2, and you are implementing these states preparation and these measurements and so on, so on, so on. If the provider has failed to meet all these conditions, the process that you are buying might not be secure. Here, I want to make protocols where I don't make any assumption about what is going on inside the box. I get a box, and I want to make a protocol based on boxes. This is why I called, and the title of my talk was Quantum Information Theory with Black Boxes. So I want to make a new form of information theory with quantum black boxes. So in this, but okay, I have to model this. Okay, now I have to tell you the tools that we need to make this new form of information theory. So when you go to the provider, you will get a box, but you want to do some actions with this box, okay? And I will label these actions in a very abstract way as when you go to the provider gives you the box, and you have some buttons. It can be a button or whatever, or it can be just a knob that you can put in different positions. So you have the possibility of doing some actions to your box, which is pressing button 1, pressing button 2, pressing button 3, pressing button 4. You don't attribute any meaning to this action. You don't know what pressing button 1 means inside the box, but it's just an action that you can do from the outside. So there is the box. It has these buttons that you can press, and as a result of you pressing this button, you can think that below the box there are some lights, and one of the lights is on. Well, this is a way of seeing this. What I'm saying is that in the box you have the possibility of doing something and getting something. If you want to think about it, you can press a button and you get a result. So we label this by you can put classical information inside the box, and you get classical information out of the box. Again, you can press a button and see that some light is on. And whenever you press a button, you get a result. So if Moises and I want to make cryptography, we go to the provider and we ask a box with buttons. The provider can always do that. And we go and we test these boxes. So we want to be sure that the provider is not cheating, and want to make sure that these boxes behave in the right way. And the only thing we can do is just pressing buttons and seeing the result that is obtained after we press a button. And this is something that we can test. We don't have to put any trust in the provider. I can go to my lab, he can go to his lab, and he can press button and observe the results. And at the end of the day, we can repeat this many times. We can count how many times I get result A and B when I press button X and Y. We count these frequencies, and this is just a probability of getting result A and B given X and Y. Again, I don't have to put any trust in the provider for that. I go to my location, I spend some time pressing buttons and observing the results. How the box produces the output A given the classical input X, I don't care. There is a process there that is taking place. What I care is about the numbers, these numbers that I see. If I can make cryptography only based on this, then I don't have to put any trust in the provider. Because if I don't see the good numbers here, I give the boxes back to the provider. Okay, I hope it's clear what I meant. And this is what we call device-independent cryptography, okay? Because you want to make protocols independent of the physics of these devices, okay? If for you it's irrelevant what the inner working of the devices, how the output is produced given the input. Okay, so I think this is the good thing is that now you don't have to make any assumption about what is happening in the device, okay? In contrast to standard QKD, where you have to assume that you prepare things in a Hilbert space of dimension 2 and things like this. Here, I don't want to make any assumption. Good. I can skip this. Okay, now, well, okay, no, maybe. So this is, I presented this in terms of cryptography because this is what basically motivated us to consider this scenario, but I see it in a more general way. So I want to do an information theory where devices are just seen as black boxes and see how far I can go with this. Of course, the model has some limitations because I'm not making any modeling of these devices, okay? And then this is something that has clear limitations because sometimes it's good to know a bit better what is happening here to make things with these boxes. I want to see how far I can go with this description. Okay. So I hope it is clear that first, quantum information theory represents a change in the things you can do about information, because you make information protocols, in particular information cryptographic protocols based on physics. I hope it is clear that at the same time, if you base a lot your devices on the physical details of your devices, this opens some problems in some applications, especially for cryptography. And this is why we needed to consider an information theory with black boxes. So this was my motivation. Now I will tell you why we can do things in this scenario. Okay, so I think at first sight, it might seem a bit difficult to make things with black boxes. Okay, but now I will tell you why we can do things. And this is the second main message of my talk. So the nice thing why we can do things in this protocol, we can prove theorems and conclude that protocols are secure, is because, okay, we don't assume anything about these boxes, but we assume that they are physical boxes. So they can do many weird things, but they have to be compatible with the laws of physics that we know today. And here's the message. As you will see, this is important because physical principles impose limit on correlations. And by correlations, I mean this. I mean, correlations, when I mention correlations, I mean how the statistic that this person sees in her device is related to the statistics that this person sees in his device. Okay? These devices have to be correlated, and this I will express by this probability distribution, and this is what I will call correlations. So my second main message is to show you that if I assume that these devices are physical, these probability distributions cannot be whatever. They have some non-trivial mathematical structure that I can use to make information protocols. Okay, so in principle, what are these correlations among the devices? These are probabilities, so these are numbers that are positive and they sum up to 1. But now let's put some physics. So I assume I have a device here, Moises has another device, and we are far apart, and we know that our devices don't communicate, okay? Well, this means that if the devices don't communicate, we can impose what is called the no-signaling principle. So the no-signaling principle is nothing but, you can understand it as the same as Einstein causality that tells you that there is no faster-than-light communication. So, for instance, in the case of two devices, it means that what the statistics that you see in this device cannot depend on what the other device is doing. Okay? Why? Because if this person could modify these statistics by doing some actions here, they could use this to make faster-than-light communication. So if I could modify what Moises sees from my location by just pressing button in my box, I could send information to him. Because if I want to send a 0, I press button 1. If I want to send a 1, I press button 2. And if with this action I'm able to modify what he sees, by looking at his box, he will be able to infer what I pressed. Okay, so this will be a way of communicating, and we can do this process even faster than light. Okay? So these boxes can do whatever you want, but we assume that we cannot use them to make faster than light communication. So this means that what I see cannot depend on this action. So if I sum over all the results, so if I sum, what this person sees is just the sum of these probabilities, sum over these results. Cannot depend on the input. Because again, if it was the case, these devices would violate Einstein causality. And this gives some non-trivial mathematical constraints on these numbers. They have to satisfy these conditions. Okay, good. Second thing. Now let's think about what correlations we can see with classical devices. So what is a classical device? Moises and I go to the provider, and the provider writes a computer program that tells the outputs given the inputs. So you can think that a small daemon that is inside the box with some instructions, and the daemon sees the input and looks at the instructions, and depending on the input, produces the output. So this is a way of producing correlations. So someone wrote some instructions in the boxes, he puts the instructions in one of the boxes, he puts the instructions in the other box. These boxes, I get one, Moises gets another one, and the boxes display correlations because they were prepared in the same location. Well, you can see that then the correlations that you can get can always be written in this form. So there is some lambda inside the box, and these are the instructions, and depending on the lambda and the input, you produce the output. Again, this seems super natural, because what you see at box, say 1, is just a deterministic output of the input and something that was written inside the box in the past. Again, it does not depend on what the other boxes do, okay? Otherwise, I would violate Einstein causality. Well, for those who know, these are nothing by the Einstein, Podolsky, Rosen correlations, local hidden variable model, you name it, okay? But it's just the standard correlations that we expect in our classical macroscopic Newtonian world. Okay, but we are quantum physicists, so we believe that devices are quantum. So what I should see if the boxes are quantum, I should be able to write them in a quantum language. Now, if you go to a textbook, the textbook will tell you that quantum correlations can always be written like this. So are just measurements acting on a quantum state. So there's a measurement for box 1, another measurement for box 2, another measurement for box 3, and so on, so on. And these boxes are different, so I put a tensor product, and this is acting on a quantum state. Well, this formula may sound familiar to you. If not, you shouldn't care about it. What I'm saying is that quantum physics tells you that the correlations that you should expect in nature should be written in this form. So I would say that some correlations are quantum whenever there exists a Hilbert space where I can find a vector and measurements that I can combine according to how the textbook tells me and produce these correlations. And I can tell you this is also a non-trivial mathematical constraint on your numbers. Okay, so I was telling you about these correlations that you can get between physical devices. So there are these correlations that are compatible, if you want, with Einstein causality, that we call no signaling. There are the correlations, classical correlations, and there are quantum correlations, those that I can get by making measurements on quantum particles. So these three definitions, no signaling, classical, and quantum, define sets of correlations. And I can represent this pictorially in this way. So this is the set of classical correlations, those that we see in our macroscopic world. This is the set of quantum correlations, the red one. Okay? And there is the set of no signaling correlations, those that are compatible with Einstein causality. So it's proven that if you zoom in this region, it's proven that the set of classical correlation is strictly smaller than the set of quantum correlation, which is strictly smaller than the set of quantum correlations. Okay, I'm not going to work here. I believe that I want to work with quantum correlations. So I'm going to work in this part of the region. Okay, we can. And how do we know that quantum correlation is larger than the classical correlations? This we know because Bell proved that back in 1964. Okay, so that was the proof that quantum physics is. This is the final proof that quantum physics is something beyond classical physics. Because there are these points here, you can observe correlations between particles in quantum physics that you cannot explain with classical physics. So for that, I have two mini courses in my talk. One is about quantum cryptography, I already told you, and the second one is about Bell inequalities. So what is a Bell inequality? It's just this boundary between classical correlations and quantum correlations. So you see, this is a Bell inequality. All the classical world is at this side of the Bell inequality, this hyperplane here, while there is a quantum region beyond this hyperplane. So I used this slide yesterday for a talk that I gave here, but I will use it again. So let me just explain what is a Bell inequality. So again, I always use boxes. So imagine this experiment. There is a source, this provider in my previous explanation. So Moises and I go to the provider, or we ask a provider to send us particles. So the provider sends me a particle, he sends a second particle to him, and once we get the particle, we make two measurements, and we get an output. And I will label this output plus and minus 1. And I will label the measurement I implement 1 and 2. I don't give any meaning to this measurement. I do an action to this particle. And as a result of this action, the particle gives me a result. So I will call A1 the result of a particle at Alice's location when I use input 1, and A2 is the result when I use input 2. The same for B1 and B2. So this is just an experiment where I can use here either 1 and 2, and I get plus or minus 1, and the same here and here. And if I see correlation, they should come from the fact that these two particles were prepared in the source. So now I take this combination of, okay, it might sound a bit weird why I take this combination, but it works. This is why I take it. So I take this combination. Whenever this person measures 1, I mark the result, and then I also take those cases where this person also measures 1 and take the result and compute the product. This is A1B1. And I do the same for A1B2, A2B1 minus A2B2. Now, this is something that you don't need any deep mathematics to do. If these are plus and minus ones, you can see that this function here can take value plus and minus 2. Okay, these are all the values you can take. If you want to see an example, well, this is very simple to prove. You take all possible combinations of plus and minus ones here, and you will see that it's plus 2 or minus 2. There is no, you don't need any group theory to make this calculation or anything like this. It's just simple mathematics. So for instance, if you impose that A1 is equal to A2 is equal to B1 is equal to B2 is equal to plus 1, this is equal to plus 1, plus 1, plus 1, minus 1, this gives 2. So in our classical way of understanding correlations, where everything was prepared at the source, the value of this quantity has to be at most 2. Okay, believe me, if you go to quantum physics, you prepare here 2 particles in this state and you implement these measurements, you get 2 square root of 2. Okay? So this tells you that there is no way of explaining this experiment by assigning definite measurement outputs to the measurements that you're going to implement. And this is why we say there is no classical explanation for this experiment. And this is precisely this region here, where quantum physics is different from classical physics. Okay, so this is what I was saying. Okay, so if you take this scenario, CHSH equal to 2 is this, so all classical physics is here. Quantum physics happens to be between 2 and 2 square root of 2, and I can tell you that no signaling is here. It can go up to 4. This is why we know there are some points that are not even quantum. Okay, so new type of cryptography. We want to make cryptography with black boxes, and we can do cryptography with black boxes because these black boxes have to satisfy some physical principles. Okay, so if we want to do an information theory with these black boxes, and we believe in quantum physics, we have to characterize quantum black boxes. And this is what we did in this series of papers some years ago. So the question is very simple. So now I want to understand which correlations quantum black boxes may display. Okay, so I want to know when some correlations that I can see in the lab can be written in this form. So imagine, for instance, you are an experimentalist, you have an experimental group, and you are doing quantum experiments. You believe you are doing quantum experiments, and then you have a PhD student, and the PhD student comes to you, and the student says, look, I made an experiment, I was checking correlations between 2 particles, and I got these numbers. Okay, I can tell you these numbers are positive, they sum up to 1. Why not? It could be that the guy makes the experiment and gets these numbers. So, and now you wonder whether they can, and the student says, I got these numbers, but I don't know how to explain these numbers. So what do you do with the student? You fire him or you keep him? I mean, what do you do with these results? So the question is whether these numbers can be explained with quantum physics. So you see, it's a very simple question. I just give you these numbers, and now I ask you whether there is a quantum experiment that can give rise to these numbers. Okay, so I can prepare a state, send it to 2 different locations, and make experiments here, measurements, so that the correlations they display are given by this. Again, why not? So a way that you can do with this, you say, okay, I suspect that in my experiment I'm dealing with spin 1/2 particles, so I will try to do it with Hilbert spaces in dimension 2. And I can tell you will fail. Okay? Now you can say, oh, maybe I was too naive thinking that my experiment was doing dimension 2. I will try with dimension 3. I can tell you that you will fail as well. And then you can say, well, I can try with dimension 4. Well, you understand that you are not going to run all possible Hilbert spaces, okay, up to dimension infinite dimension. So we should find a way of excluding all possible quantum explanations. Well, this is what we did in these papers. Okay? So basically, we could prove that the point is here. So there is no quantum explanation for that. Of course, this is not happening because if this happened, we could prove that quantum physics is wrong. And at the moment, this is not happening. But for us, it's good because we understand this limit. If we want to make information theory with quantum correlations, we have to understand the limits on quantum correlations. Okay, so now we have something, and we can test that. We can test the limits for quantum correlations. Okay, so now I will combine all these things to give you a hint of why we can make protocols. Okay, and I will come back. I will illustrate this with the problem of randomness, which is very much related to the problem of cryptography. And I will use an example that I like very much. So imagine you have a virtual casino, okay? And you have a web page, and there you have a virtual casino. And you want to make money. And of course, you know that to run a virtual casino, you need a good random number, okay? Because if you use things that can be predicted, you won't make any money, okay? So you need a random number to run your virtual casino. So you come to me, and I'm a quantum physicist, and you have heard about something called a quantum random number generator. Okay, so you come to me, and you say, okay, I want a random number generator for my virtual casino. I know you have a virtual casino. And then you say, I want a random number generator. And then I say, look, I really have what you need, okay? So I have a random number generator which is based on quantum physics, and you can buy this. I will charge you twice the price of a normal random number generator, but it's secured by quantum physics. And you say, okay, I buy it. So what I do when you come, I have a quantum random number generator. I generate the random numbers before you come. I copy these random numbers into a classical memory. I put this classical memory into a box. I paint this box in fancy colors, and I write quantum random number generator. And I sell this to you. Okay, you look at the box. It's written quantum random number generator. I look like a nice guy, possibly, so you trust me. But you don't really trust me. I'm Spanish, you know. You should never trust Latin people. So what you do, you say, okay, I want to make sure that this person is reliable. So you start generating some random numbers. And I can tell you that they will pass any statistical test that you run in these random numbers because I generated them with a proper random number generator. So you say, well, a good guy, I mean, I trust him. And now you use these random number generators for your virtual casino. Of course, these random numbers are random to you, but they are not random to me because I generated them, I don't know, many weeks in advance. So I wait for this moment, and then I can take all your money. Remember the joke about Dilbert, okay? You can never trust a box is random. Well, now you can, okay? Because what you have to do, this is because we think in classical terms. So you have to come to me, and you don't have to ask for one box. You have to ask me for 2 boxes. And now you run, for instance, this experiment with your boxes. So you ask me for 2 boxes where you can put information and get information. And you ask for a violation of CHSH. And this is something you don't have to put any trust. You just buy and press buttons and get output. Now, if the boxes I'm giving you don't violate CHSH, then you don't know whether they are quantum. They might be classical. So they might not be random. So if they don't violate Bell inequality, you give them back and say, I don't want your boxes. This is not what I wanted. But if they do violate a Bell inequality, you know because that you are in this region. So there is no classical explanation for your boxes. So you know for sure that your boxes are quantum, and indeed, I'm not going to tell you how, you can prove that they are random. And in fact, this is what we did some years ago. You can relate the amount of Bell violation with the randomness in the box. This is a technical part, and for that, we use the techniques I was telling you about bounding quantum correlations. So this is the region. Remember, the CHSH was bounded by 2, and this is the predictability of your outputs. So the point where you don't violate the inequality, remember the bound was 2. The predictability is 100%. There is no randomness. But as soon as you start violating the inequality, you have some lack of full predictability that you can use to generate proper random numbers. And this is the only reason why we can establish this curve is because all this region here is impossible with quantum physics. So there is no Hilbert space where you can produce, there are no 2 quantum boxes that the provider can prepare for you in which you see this Bell inequality violation and the provider can predict your outputs. It's impossible. If it was possible, quantum physics was wrong. Again, it's just physical security. If you trust quantum physics, the two boxes that give a Bell inequality violation are certified to be random by quantum physics. And I don't have to put any trust on the provider. I don't have to believe that the provider has prepared spin 1/2 particles, bosons, fermions, you name it. No quantum preparation can give this Bell inequality violation and is able to fix the output. And this is why you can do things in this scenario. Okay, I wanted to make the talk hopefully very clear and slow, so I had many things to explain, but I'm not going to do it. So my talk was about theory. What I can tell you, I think device independent is something very nice because it gives you this self-certification black box approach to quantum information theory. Just a short message, it's demanding. So from the point of view of technology, you have to prepare boxes that violate a Bell inequality. And you have to do it, for the experts, closing the detection loophole. And this is something that has been done last year, but it's not super easy. Okay, so this is demanding. But there are some solutions. I could have told you about it, but I'm not going to do it. Okay, as you see, I have many things. I can tell you many things. Okay, last thing I want to tell you, do I have 5 minutes? Okay, so then I will tell you the last thing, okay? So in a way, you can understand, all what I was telling you is, what I did was the following. So I had a quantum information problem, which is the design of cryptographic protocols with boxes. And to solve this problem, I used Bell inequalities, which is something that was invented or was derived in a context of quantum foundations. People wanted to understand the difference between classical physics and quantum physics, and they derived Bell inequalities. So it's an application of quantum foundations to quantum information theory. So one of the reasons why I like this approach to quantum physics, this black box approach, is because you can also use quantum information concepts to say things about quantum foundations. This is not what I'm going to say. I'm going to illustrate with this last paper. This is the last thing I wanted to tell you about, which is the paper that we published last year and something called almost quantum correlations. Okay, so if you follow my explanation, I was telling you that we can conceive 3 different sets of correlations. One, which is what you can do with classical physics. The other one is what you can do with quantum physics. And I was telling you that in principle, we could conceive some other correlations in nature without violating any faster than light communication. Okay, this is the region here, where you could in principle violate quantum physics. Actually, why not? How do we know that quantum physics is the last theory of nature? We could think that some particles can show some correlations that go beyond quantum physics. And what I'm going to tell you was started with a seminal paper by Popescu and Rodríguez. So who knew about the region of this, about the existence of this region? Okay, and the reason why they knew about this region is because if you take CHSH, I was telling you that the classical bound is 2, and quantum physics can go up to 2 square root of 2. But they knew that with beyond quantum physics, you can go up to 4 without any faster than light communication. So in principle, I can give you some correlations, some probabilities that look very innocent, but they are not because we don't know how to do them with quantum physics. So now if you tell me, Tony, how do you know that these correlations are not possible in nature? The only explanation I can give you is that, well, we believe that they are not possible in nature because I don't know how to do them with quantum physics. But if you think about it, the fact that I don't know how to do them with quantum physics means that I cannot find a state and measurements in a given Hilbert space that I combine with a Born rule so that I get these probabilities. Okay, this might be satisfactory, but for some people it's not the nicest answer you may think for this question. Okay, the fact that I cannot find objects in a Hilbert space. So people thought, okay, maybe we can understand why these super quantum correlations, we don't see them in nature without thinking about the Hilbert spaces. And there is a very nice result by a computer scientist called Wim van Dam that he published in this paper, who considered the following problem. Let's assume that these correlations exist in nature. Okay, why not? Let's assume that we have boxes that have these super quantum correlations. What could we do with them? And Van Damme, who is a computer scientist, he considered a problem of communication complexity. So what is communication complexity? So let's imagine that I have to find a day for my talk with Moises. I'm in Spain, he's in Mexico. So we have to find a date in our agendas. So you understand that for that we need to exchange some communication. So I can say, I'm free on Tuesday, and he will say, oh, no, we cannot be on Tuesday. What about Thursday? And then I will check my agenda, I will say, I can do it on Thursday. So we need to exchange some communication. So this is an instance of a communication complexity problem. I have some data, a friend of mine has some other data, and we have to solve a function, we have to compute a function of our data. Of course, a trivial solution is I get all the data from my friend and I compute the function locally, but this is expensive. So communication complexity studies how much communication you have to exchange to solve a function that depends on two distributed set of data. So we expect that there are functions that are difficult to compute. So there are functions for which I will have to send a lot of my information for my friend to be able to compute this function. In this sense, it says that communication complexity is not trivial. Things scale, there are some problems for which things scale with the complexity of our data. Okay, so Wim van Dam proved that if you had these supra quantum correlations here, communication complexity would become trivial. So we could solve these problems just sending a few bits to the channel. Well, we believe this would be too nice to be true. Okay? So instead of talking about Hilbert spaces, he argued that the reason why this point here does not exist in nature is because if these correlations existed, then communication complexity would become trivial. As we believe that communication complexity cannot become trivial, these correlations are not possible in nature. And then people tried to, okay, this was only for that point there, and people then tried to understand whether we can get the quantum boundary just by reasoning in terms of information principles. Okay, what we prove in our paper is that this might be difficult. Okay, but I just wanted to tell you briefly about this because I think it's something very nice. So you try to understand about theories beyond quantum physics in terms of information principles. Okay, so that was a long trip, and I think it's good to conclude. So I was telling you about why I think this device-independent approach, this black box approach to quantum physics, to quantum information is interesting. It provides certification, and you don't have to trust your provider. So you can make cryptography without trusting your provider. So for that, you have to certify that your boxes are quantum, and the only way you can certify that some boxes are quantum, you have to exclude any possible classical explanation. And the only way you can do that is by the means of the violation of a Bell inequality. So the observation of non-locality of Bell inequality violation is a necessary ingredient for that. Not sufficient, but necessary. So we have protocols for randomness generation. I briefly told you about this idea of you getting two boxes and generating randomness out of this. Also cryptography and some other protocols. But somehow one of our main interests is to understand what you can do in this regime. I didn't tell you about this, but I just briefly mentioned that from a technological point of view, things are challenging. Not impossible, but challenging. And also the nice thing is that it gives you new ways of tackling questions in foundations, like understanding how you can try to think of situations where you go beyond quantum physics. Okay, I conclude. Thank you very much.
We have enough time for questions. Any question or comments?
I remember that it had been extremely sophisticated experiments to prove the Bell's equality a couple of years ago. And if I understood you correctly, to some extent you have to use this in your black boxes. Mm-hmm. Yes. And what may be the experimental state changed in the last years? So what is the idea? Will it be possible in near future to build such boxes or not?
Okay, so again, in this device-independent approach, you are super paranoid. Okay, this is why it's good for cryptography. So you think that among all possible explanations for your experiment, the worst is happening. Okay. So this is why Bell inequality violations in the past, I mean, there were Bell inequality experiments, like there is a famous experiment by Aspe in 1982, okay? That was enough, say, for an average physicist. That was enough to conclude the Bell program and prove that quantum physics was beyond classical physics. So what happens in the Aspe experiment, for instance, is that he was making an experiment with photons, and it's very difficult to have good single photon detection efficiency. So he, in the experiment, Aspe and co-workers, missed many of the photons. So many of the times, the result was no click, no photon. So if you are paranoid, you can design a classical explanation for the scheme. So the scheme is a bit weird. So in the scheme, in this classical explanation, the photon goes to the measurement, looks at the measurement that you're going to implement, and decides to click or not to click. It's weird. We think that photons don't click or not to click independently of the measurement you implement. It's just a matter of the detector, okay? But it was in principle possible to give a classical explanation for a space experiment, but for that you needed to assume somehow that in your classical model, the photon goes and decides to click or not to click depending on the measurement of the polarized beam splitter that you put in front of it, okay? Which is, we don't think to be the case. So this is why a space experiment in many ways was enough to conclude the program, but if you are really paranoid and you want to exclude any possible explanation, you have to do experiment with higher detection efficiency. And this is what was done last year. Okay, or in the past year, there were good experiments showing Bell inequality with super high detection efficiency so that this not so natural classical explanation was not possible either. Now, if you want to do things in this scenario where you don't want to trust the provider, you have to think that the worst is happening in your boxes. So you have to do it with high detection efficiencies, which is challenging, but has been done. So it's possible already with current technology. So in principle, I'm not saying at the commercial level, but in principle, the random number generators I was telling you about with 2 boxes can be done with an experiment with photons.
Thanks.
Any other question?
Yeah. Is there any way to quantify the degree of quantumness? I mean, you are providing a certificate to say if it is quantum or not, but in a real experiment, you typically, even if you design a quantum experiment, you typically have decoherence. So maybe you have something in between which still preserves quantum effects, but it is spoiled by decoherence. So is there any way to certificate some degree of quantumness?
Okay, so in a way you can think that the amount of violation of your Bell inequality is a possible quantification of the degree of quantumness. But okay, for me a Bell inequality is first a witness or a certificate of quantumness, because something you cannot violate a Bell inequality with classical physics. So you violate a Bell inequality, you have quantum devices. In a way, one of our results in all this is also a quantification of quantumness, and I quantify quantumness by the randomness I get. We also know that in classical physics it's impossible to get random stuff, okay? Because at the end everything is a deterministic. Classical physics is deterministic. Okay, there are some issues with chaotic models, but at the end everything, if you have perfect knowledge about your initial conditions, you can predict everything that happens in the future, which is not the case in quantum physics. So the Bell inequality was a test of quantumness, and we could even measure the randomness produced in the setup, the quantum randomness measured in the setup. If you remember my curve, I was showing you a relation between Bell inequality and randomness. So you can see this measure of randomness based on a Bell inequality as a measure of quantum randomness, and therefore as a possible way of quantifying the quantumness of your setup. So the reason why we can do things is because we can move from detection of quantumness to quantitative statements, like amount of randomness, amount of secrecy. I didn't tell you about this, but amount of secrecy. I can make links between Bell inequality violation and amount of randomness, amount of secrecy, and and operationally relevant quantities.
Another question? Well, yes? No. If not, well, we thank again our speaker. I have two announcements. First, if you want to go to the museum, the meeting will be at the lobby of the Gilo Hotel at 2 p.m., as I know. And the other is, if concerning with the closure session, please contact the organizer of your symposium.